Today we're going to take a look at stretching and compressing graphs. So that's towards the bottom of this kind of cheat sheet of transformations. Again, as a reminder, anything that is outside the function is vertical and normal. So right here, if you are multiplying the function by a value greater than 1, it's a stretch. That makes sense. If you're multiplying the function by a value between 0 and 1, that is a compression. You're making it smaller, you're shrinking it. However, for the horizontal stretch and compressions, it's the reciprocal. It's the opposite of what you think. Not the opposite as in positives or negatives, the opposite of what you think. So if you are multiplying by a value greater than 1, it's actually a compression. If you are multiplying by a value between 0 and 1, it's actually a stretch. So notice inside the function is already the reciprocal. And I'm talking about what you actually see. If you actually see a number greater than 1, it's a compression. If you actually see a value between 0 and 1, it is a compression when it's grouped with the x. So we'll start with vertical because that's easier because it's normal. And we've got 3 times x squared. So identify that parent function, have that graph in your mind, what it should look like. Critical point because it's just a stretch, 0, 0. When you multiply it, stays at 0, 0. Domain, it's parabola, all real numbers. Range, the critical point didn't change, so we've still got greater than or equal to 0 because we don't have any reflections on this one either. So our setup for this one is a bit more complicated. I like to use the parent function and then stretch it and use those as directions. Or in this case, because we're not shifting, they will actually be our ordered pairs on the graph. So substituting into the parent function, squaring these values. And then depending on if it's a vertical or horizontal stretch or compression, I will change or multiply the correct t-table value. So this is a vertical stretch, so my x values stay the same. My y values get stretched vertically by 3, so I'm going to multiply my y values, my parent function y values, by 3. Maybe I should actually multiply them. And then the last 2 columns right here, sorry about that, will be my directions, or in this case, because my critical point didn't change, those are my t-charts, my xy ordered pairs. So starting at the origin, all of these are going to be scaled by 2. The first one was negative 2, 12. That one doesn't quite fit on the graph, so I'm going to do negative 1, 3. Reflecting that, I get 1, 3. And then 2, 12 also didn't fit on the graph. I'm going to kind of try and approximate where those might be so I have a better idea of where to aim. These vertical stretches make your graph pretty skinny so they don't fit real well on the coordinate plane. Now we're going to look at a vertical compression. We're looking at multiplying by a third. Our parent function is the absolute value. So have that v in mind as we're graphing this one. Critical point doesn't change with just a stretch or compression. Domain, you can still take the absolute value of all real numbers. No reflections, so our range is still greater than or equal to 0. So for our parent function values, all of these will become positive. It's still a vertical compression, so my x values stay the same. And I'm going to multiply my y values by my compression of 1/3. And then I'm going to plot those points to get the graph of my absolute value. This time, because I've got those fractions, I'm going to call each of these 1. Starting with my critical point, and I'm supposed to go left 1, up 1/3. So that'll be about here. Left 2, up 2/3. And then right 1, up 1/3. Again, using that line of symmetry. and getting that V function. So make sure you're also thinking about whether the graph matches the transformation you've identified. This is a vertical compression. It's getting squashed vertically, and you can see that happening with this graph.